Hello, everybody. In this episode, I'll be speaking with Vikrant Varma, a research engineer at Google DeepMind and the technical lead of their sparse autoencoders effort. Today, we'll be talking about his research on problems with contrast-consistent search and also explaining grokking through circuit efficiency. For links to what we're discussing, you can check the description of this episode, and you can read the transcript at axrp.net. All right, well, welcome to the podcast.
Thanks, Daniel. Thanks for having me.
Yeah, so first, I'd like to talk about this paper. It is called Challenges with Unsupervised LLM Knowledge Discovery. And the authors are Sebastian Farker, Zachary Kenton, Johannes Gasteiger, Vladimir Miklik, and Rohin Shah. And this is basically about this thing called CCS.
Mm-hmm.
Can you tell us, what does CCS stand for and what is it?
Yeah, CCS stands for contrastive consistent search. So I think to explain what it's about, let me start from a kind of more fundamental problem that we have with advanced AI systems. One of the problems is that when we train AI systems, we're training them to produce outputs that look good to us.
Yep.
And so this is like the kind of supervision that we're able to give to the system. And we currently don't really have a good idea of how an AI system or how a neural network is computing those outputs. And in particular, we're worried about the situation in the future when the amount of supervision we're able to give it causes it to achieve a superhuman level of performance at that task. And we can't, by looking at the network, we can't know how this is going to behave in a new situation. And so the Alignment Research Center put out a report recently about this problem, and they named this problem as, or they named a potential part of this problem as eliciting latent knowledge. And what this means is, if your model is, for example, really, really good at figuring out what's going to happen next in a video, as in it's able to predict the next frame of a video really well, given a prefix of the video. This must mean that it has some sort of model of what's going on in the world. And instead of using the outputs of the model, if you could directly look at what it understands about the world, then potentially you could use that information in a much safer manner. Now, why would it be safer? So consider how you've trained the model. Supposing you've trained the model to just predict next frames, but the thing that you actually care about might be, is your house safe, or is the thing that's happening in the world a normal sort of thing to happen, a thing that we desire? And you have some sort of adversary, perhaps this model, perhaps a different model, that is able to trick whatever sensor you're using to produce those video frames. Now, the model that is predicting the next video frame understands the trickery. It understands what's actually going on in the world. This is an assumption of superhuman systems. However, the prediction that it makes for the next frame is going to look very normal because your adversary is tricking the sensor.
Yep.
And what we would like is a way to access this implicit knowledge or this latent knowledge inside the model about the fact that the trickery is happening, and be able to use that directly.
Sure. And so I take this as kind of a metaphor for an idea that, like, we're going to train AI systems. We're going to train it on an objective of, like, do stuff we like. And the notion of, like, we imagine that we're, like, measuring the world in a bunch of ways, right? We're looking at GDP output. We're looking at, like, how many people give a thumbs up to stuff that's happening. Various sorts of ways we can monitor the performance of an AI system. And an AI system could potentially, like, be doing something that we actually wouldn't approve of if we understood everything correctly. But, like, we all give thumbs up to it.
That's right.
And so, like, ideally we would like to somehow get at its latent knowledge of what's going on, rather than just, does it predict that we would thumb up a thing, so that we can say, like, hey, do we actually want the AI to pursue this behavior, or like, are we going to reinforce this behavior rather than just reinforcing things that in fact would get us to give a thumbs up, even if it would suck in some way?
That's right. So one way you can think about this problem is we're trying to improve our ability to tell what's actually going on in a situation so that we can improve the feedback we give to the model.
Yep.
And we're not able to do this just by looking at the model's outputs or the model's prediction of what the world will look like given certain actions. We want the model to connect the thing that we actually care about to what's going on in the world, which is a task that we're not able to do.
Sure. So with that out of the way, what was this CCS thing?
Yeah. So CCS is a very early proposed direction for solving the problem of eliciting latent knowledge. And in brief, the way it works is, so supposing you had a way to probe a model to tell you what it believed about some proposition. This is the kind of ideal thing that we want. Supposing you had a solution to ELK.
Yep.
Then one property of this probe would be that the probability that this probe would assign to some proposition would satisfy like the laws of probability. So, for example, it would satisfy P of x equals 1 minus P of not x.
Yep.
And so you might try to use consistency properties like this to search for probes that satisfy them.
Sure. And to be clear, by probe, you mean like a learned function from the activations of the neural net to like a probability or something?
Yes. So you could have probes of different levels of complexity. The particular probe used in CCS is a kind of very simple linear probe on the activations at some site. Yes.
Sure. So the idea is there are some properties that are true of like probabilities, like the probability of x is 1 minus the probability of not x.
Mm-hmm.
And the hope is we like train a probe to sort of fit the laws of probabilities and stuff. And hopefully that will get at the model's beliefs, because the model's beliefs will be probabilities.
That's right. Yeah. So there's a lot of subtlety here. So the thing I described is true of the model's sort of true belief or true probabilities that it's assigning to things.
Yep.
It's also true of many other types of things that the model might be computing. And this is really a core of the problem that we pointed out in our challenges paper. So I could go a bit into the problems, or I could go a bit more into how CCS itself works.
Yeah, just tell us how CCS itself works so that we have a sense of like what we're talking about.
Okay. So mechanistically, what's going on in CCS is that you take a set of factual yes or no questions that you think the model knows the answer to. So an example of this is IMDb movie reviews, where you're fairly sure that a model of a certain size knows whether the sentiment in the review is positive or negative.
Gotcha.
Now, for each item in this data set, so for each review, you construct a contrast pair by appending, for example, the string, this review is positive or this review is negative to that item.
Okay.
And now you take the difference in the activations when you run these two contrast pairs through the model. So I'm going to call these contrast pairs as having different charges, as a positive charge and a negative charge.
Okay.
So you're constructing these contrast pairs with these pairs of activations, and then a thing you can do is you can cluster them. So when you're clustering the difference in the like positive and negative charge, the thing you will find, or the thing you might hope to find, is whether the model thinks that the charge that was appended to the statement is true or is false. And these two things will point in different directions. And so that's why you might hope that you could separate them.
Yep.
Now, CCS is slightly different from this in that it doesn't directly do the clustering. Instead in CCS, you learn a probe that directly outputs a probability of that statement being true. And then you're training the probe using this consistency property. So the fact that the two opposite contrast pairs should be like the negation of each other.
Gotcha. And am I right that before you take the contrast pairs, you like take all of the positive charge activations and like subtract off their mean and divide by the standard deviation,
That's
so
right.
that the differences aren't just pointing in the direction of like, is the review, or is the thing at the end saying this review is positive versus this review is negative?
Yes, that's right.
Right.
So this is another pretty subtle point. So one problem with this general method of classification is that if there are other differences that are salient between the two contrast pairs that are not just did I construct a true statement or did I construct a false statement, then you might end up separating your clusters based on those differences. Now, one obvious difference between the two contrast pairs is that you've appended a positive charge and you've appended a negative charge. And so that's a really straightforward one that we have to fix. And the method proposed in the CCS paper to fix that is that you take the average sort of positive activations and the average negative activations, and you subtract those off. And so you might hope that the thing you're left with is just the truth sort of value. It turns out that in practice, it's not at all clear that when you normalize in this way, you're left with only the truth values. And one of the experiments we have in our paper is that if you introduce distractors, so for example, you put a nonsense word like banana in the middle of half of the, or at the end of half of the reviews, and you put a different nonsense word like shed at the end of the other half of reviews. Now you have this kind of weird other property, which is like, is your statement banana and positive charge, or is your statement banana and negative charge? And this is obviously not what you would hope to cluster by, but it turns out that this is just way more salient than is your review positive and is your review like, does your review have positive sentiment and did you append a positive charge? Which is the thing you actually wanted to cluster by.
Yep.
Yeah, so this is an important point that I wanted to make, that this procedure of normalizing it's actually quite unclear whether you're able to achieve the thing you wanted.
Sure. So before we talk about the experiments, I'd like to talk about just like, so like in your paper, first you have some theorems, then you have some experiments, and I think like that's a good way to proceed. So theorems 1 and 2 of the paper, I read them as basically saying that the CCS objective, it like doesn't really depend on the propositional content of the sentences. So if you think of the sentences as being like, are cats mammals? Answer yes, and are cats mammals? Answer no, or something. Like one way you could get low CCS loss is to basically be confident that the yes or no label matches the proposition of whether or not cats are mammals. And I take your propositions 1 and 2 is basically saying, you know, you can just have any function from sentences to propositions. And like, you know, so for instance, maybe this function maps are cats mammals to is Tony Abbott the current Prime Minister of Australia? And like, you know, just grade the yes or no answers based on like, you know, do they match up with that like transformed proposition rather than the original proposition? And like that'll achieve the same CCS loss. And basically like the CCS loss doesn't necessarily have to do with like what we think of as the semantic content of the sentence. So this is kind of my interpretation of the results. I'm wondering, like, do you think that's fair?
Yeah, I think that's right. Maybe I want to give a more realistic example of a kind of unintended probe that you might learn that will still give a good CCS loss. But before that, I want to try and give an intuitive explanation of what the theorem is saying. So it's saying that the CCS loss is saying any probe that you find has to say opposite things on positive and negative charges of any statement.
Yep.
This is the consistency property. And the other property is contrast, where it's saying you have to push these two values apart. So you can't just be uncertain. You can't just be 50-50 between these two. Now, if you have any CCS probe that satisfies this, you could, in theory, flip the prediction that this probe makes on any arbitrary data point, and you end up with a probe that has exactly the same loss. And so this is showing that, in theory, there's no like theoretical reason to think that the probe is learning something that's actually true versus something that's kind of arbitrary. And I think all of the burden then falls on what is like simple to extract given an actual probe empirically.
Yeah, so I take it. So if I'm trying to kind of defend the theory of the CCS method, I think I would say something like, well, kind of most of what there is to a sentence is its semantic content, right? Like if I say cats are mammals or something, like you might think that most of what I'm conveying just is the proposition that cats are mammals, and like most of what there is to, you know, model about that is, hey, Daniel said this proposition. The thing he's saying is like cats are mammals, and like, maybe the neural network is representing that proposition in its head somehow, and maybe it like, and maybe it's keeping track of, is that proposition true or false, because like that's relevant because if I'm wrong about cats or mammals, then I might be about to say a bunch of more false stuff. But if I'm right about it, then I might be about to say a bunch of more correct stuff. So yeah, like what do you make of that kind of simple case that like we should expect to see the thing CCS wants us to see?
Yeah, that's great. So now we're coming to empirically what is simple to extract from a model. And I agree that in many cases with simple statements, you might hope that the thing that's most salient, as in like the direction that is kind of highest magnitude inside activations, inside activation space, is going to be just whether the model thinks the thing that you just said is true or false. This is even assuming that the model has a thing as ground truth beliefs, but let's make that assumption. Now it gets pretty complicated once you start thinking about models that are also like modeling other characters or other agents. And any large language model that is trained on the internet just has like pretty good models of all sorts of characters. And so if you're making a statement in a context where a certain type of person might have made that statement. So for example, you say some statement that, let's say, Republicans would endorse, but Democrats would not. Implicitly, the model might be updating towards the kinds of contexts in which that statement would be made and what kinds of things would follow in the future. And so if you now make a different statement that is, let's say, factually false, but that Republicans would endorse as true, it's totally unclear whether the truth value of the statement should be more salient, or whether the Republican belief about that statement should be more salient. So that's one example. I think this gets more complicated when you have adversaries who are deliberately trying to like produce a situation where where they're tricking someone else, and so now the model is now the neural network is really modeling very explicit sort of beliefs and adversarial beliefs between these different agents. And if you are simply looking for consistency of beliefs, it feels pretty unclear to me, especially as models get more powerful, that you're going to be able to easily extract what the model thinks is the ground truth.
So sorry, why? So you have an adversary, and what? Sorry, what was the adversary doing?
So maybe you don't even need to go all the way to an adversary. So I think we could just talk about the Republican example here, where if you're making a politically charged statement that, for the sake of this example, has a factual ground truth, but that Democrats and Republicans disagree on. Now there are sort of two beliefs that would occur in the model's activations as it's trying to model the situation. One is the factual ground truth, and the other is the Republicans' belief or the Democrats' belief about the statement. And both of these things are going to satisfy the consistency property that we named.
Yep.
And so, especially when you're in a context where this is sort of like saying we have the same problem as models being sycophantic, where the model might know what's actually true, but is in a context where, for whatever reason, modeling the user or modeling some agent and what it would say is more important.
Okay. So I take this. So to me, this sort of points towards two challenges to the CCS objective. So the first is something like, the propositions might not, the sentences might not map onto the propositions we think of, right? So like, you have this experiment where you append you take the movie reviews and also you append the word banana or shed, and then you append it with sentiment is positive and sentiment is negative. And sometimes CCS is like basically checking if the positive negative label is matching whether it's a banana or whether it's a shed, rather than like the content of the review. So that's a case where it seems like what's going wrong is the propositional content that's being attached to positive or negative is not what we thought it was. And then a different kind of problem is like, or what seems to me to be a different kind of problem is like, the probe is picking up on the right propositional content. There's some politically charged statement, and the probe is really picking up like someone's beliefs about that politically charged statements, but it's not picking up the model's beliefs about that statement. It's picking up like one of the characters' beliefs about that statement. Does that division feel right to you?
I think I wouldn't draw a very strong division between those two cases. So the banana shed example is just designed to show that you don't need very complicated, or how should I put this? Models can be trying to entangle different concepts in like surprising and unexpected ways. So when you're appending these nonsense words, I'm not sure what computation is going on inside the model and how it's trying to predict the next token. But whatever it is, it's somehow entangling the fact that you have banana and positive charge and banana and negative charge. I think that these kinds of weird entanglements are not going to go away as you get more powerful models. And in particular, there will be entanglements that are actually valuable for predicting what's going on in the world and having an accurate picture that are not going to look like the beliefs of a specific character for whatever reason. They're just going to be something alien. And in the case of this, in the case of banana and shed, I'm not going to say that this is like some galaxy brain scheme by the model to predict the next token. This is just something weird, and it's like breaking because we put some nonsense in there. But I think in my mind, the difference is more like a spectrum. These are not like two very different categories.
So are you sort of thinking the spectrum is like, look, there are weird entanglements between like the final charge at the end of the thing and, stuff about the content. And one of the entanglements can be, does the charge match with the actual propositional content of the thing? One of the entanglements can be, does the charge match with what some character believes about the thing? And one of the entanglements can be like, does it match with whether or not some word is present in the thing?
That's right.
Okay. Yeah, actually, so digging in on this banana shed example, like for CCS to fail here, my understanding is it has to be the case that like the model is like basically has some linear representation of the XOR of, the thing says the review is positive and the review ends in the word banana. Right? So like there's one thing if it ends in banana and also the review is positive, or if it ends in shed and it says the review is negative. And it's the other thing if it ends in shed and it says the review is positive, or it ends in banana and it says the review is negative. So like what's going on there? Do you know? Like it seems weird that like this kind of XOR representation would exist. And like we know it can't be part of the probe because linear functions can't like produce XORs.
Mm-hmm.
So it must be a thing about the model's activations. But
Mm-hmm.
like, what's up with that? Do you know?
Yeah, that's a great question. So there was a whole thread about this on our post on Less Wrong, and I think Sam Marks looked into it in some detail. So Rohan Shah, one of my co-authors, commented on that thread saying that this is not that surprising, and I think I agree with him.
Hmm.
I think it's less confusing when you think about it in terms of entanglements than in terms of XORs.
Okay.
Um, so it is the case that you're able to back out XORs if the model is doing like weird entangled things. But let's think about the case where there's no distractors at all, right?
Hmm.
So even in that situation, the model is basically doing is true XOR has true.
Yep.
And you might ask, well, that's a weird thing. Why is it doing that? It's more intuitive to think about it as the model saw some statement, and then it saw a claim that the statement is false, and it started trying to do computation that involves both of these things.
Hmm.
And I think if you think about it, if you think about banana shed in the same terms, like it saw banana and it saw, this statement is false, and it started doing some computation that depended on the fact that banana was there somehow. Then you're not going to be able to remove this information by subtracting off the positive charge direction.
Okay. So is the claim something like so basically the model's activations at the end, they're this complicated function that takes all the previous tokens
Mm-hmm.
and puts them into this high dimensional vector space.
Mm-hmm.
That vector space being the vector space of activations. And it sounds like what you're saying is like, look, if you're just generic functions that depend both on does it contain banana or shed, and does it say the review is positive or negative,
Mm-hmm.
just like generically, those are going to include this like XOR type thing, or somehow be entangled in a way that you could like linearly separate it based on that.
Yes, that's right. In particular, these functions should not be things that are of the form like add banana and add shed. They have to be things that do computation that are not like linearly separable like that.
Okay, is that true? Has someone checked that? Because that feels like a So okay, maybe one way you could prove this is to say like, well, if we model like the charge and the banana shed as binary variables,
Mm-hmm.
there are only so many functions of two binary variables, and like if you've got a bunch of activations, like you're going to cover all of the functions. Is that roughly? Does
Yeah,
that
that's.
sound like a proof sketch?
I'm not sure how many functions of these two variables you should expect the model to be computing. I feel like this depends a bit on like what other variables are in the context, and um, because you can imagine that if there's like more than two, if there's like five or six, then these two will like co-appear in some of them and not in others.
Mm.
But a thing you can definitely do is you can back out the sort of XOR of these two variables by just linearly probing the model's activations. And I think this effect happens because you're unable to remove the interaction between these two by just subtracting off the charge.
Do you know?
And I would predict that this would also be true for like in other contexts. So I think models are probably computing like joint functions of variables in many situations, and these will kind of the saliency of these will probably depend a bit on the exact context and how many variables there are, and eventually the model will run out of capacity to do like all of the possible computations.
Sure. It sounds like based on the explanation you've given,
Mm-hmm.
it seems like you would maybe predict that you could figure out that you could get a banana shed probe from a randomly initialized network. If it's just that, the network's doing a bunch of computation and generically like computation tends to entangle things. I'm wondering if you've checked that.
Yeah, I think that's a good experiment to try. That seems plausible.
Okay.
We haven't checked it, no.
Yeah, fair enough.
Yeah.
And I guess like, sorry, I just have so many questions about this
Yeah.
banana shed thing. Like, there's still a question to me of like, even if you think the model represents it, there's a question of why it would be like so salient, you know?
Hmm.
Because like you basically, yeah, your paper has some really nice figures. Listeners, I recommend you check out the figures. I believe. Look, this is the figure for the banana shed experiment, and you show like a principal component analysis
Mhm.
of just like basically an embedding of the activation space into 3 dimensions.
Mhm.
And basically, what you show is that like it's very clearly divided on the banana shed thing.
Yes.
Like that's one of the most important things the
Yep.
model is like representing.
Yep.
What's up with that? That seems like a really strange thing for the model to care so much about, you know?
So I'll point out firstly that this is a fairly weak pre-trained model, this Chinchilla ATB.
Okay.
So this model is like not going to ignore kind of random things in its prompt. It's going to quote unquote break the model.
Okay.
That's one thing that gives you a clue about why this might be salient for the model.
So like it would be
It-
less salient if they were just like if there were words you expected, you know, the model could just like deal with it. But the fact that it was like a really unexpected word, like in some ways that means you can't compress it. You've got to like think about that in order to figure out what's happening next.
That's right. Yeah. I just expect that there's text on the internet that looks kind of normal and then suddenly has a random word in it. And you have weird things like after that point, it just repeats banana over and over, or weird things like that. And the model, when you just have a pre-trained model, you haven't suppressed those pathologies. And so the model just starts thinking about bananas at that point
Okay.
instead of thinking about the review.
And does that mean you would expect that to not be present in models that have been like RLHF'd or instruction fine-tuned or something?
Yeah, I expect it to be harder to distract models this way with instruction fine-tuned models.
Okay, cool. Okay, I have 2 more questions about that. One thing I'm curious about is it seems like if I look at the plot of like what the CCS method is doing when it's being trained on this banana shed dataset, like it seems like sometimes it's at roughly 50-50 if you grade the accuracy based on just the banana shed and not the actual review positivity. And sometimes it's at like 85, 90%.
This is across different seeds?
Across different seeds, I think. And then like if you're grading it based on, whether their view is actually positive or not, sometimes CCS is at 50-50 roughly, sometimes it's at 85-90%. But it seems like so firstly I'm surprised that it can't quite make its mind up like across different seeds. Sometimes it'll do one, sometimes it'll do the other. And it seems like in both cases, most of the time it's a 50-50, and only some of the time it's 100%.
Yeah.
So it seems like sometimes it's doing a thing that is neither checking if the review is positive or checking if the review is like containing banana or shed.
Yeah.
So firstly, does that sound right to you? And secondly, do you have a sense of like what's going on there? Why is it so inconsistent? And why does it sometimes seemingly do a third thing?
Yeah. So I think this is pointing at the brittleness of the CCS method. Someone has an excellent write-up on this. I'm forgetting whether it's Fabian Roger or Scott Emmons, but
I think Scott's doesn't focus so much on the brittleness, so it might be Fabian.
Okay. But in any case, this person did this experiment where they subtracted off. They found like the perfect direction to separate these two, the perfect truth direction that separates true and false statements, just using logistic regression, so using a supervised signal. And then once you subtract that off, it turns out that there is like no other direction, basically, that is able to separate the truth. So both logistic regression and therefore further CCS just gets random accuracy. So you might hope that CCS, when it works, is finding this like perfect direction because there's only one.
Okay.
But in fact, CCS, the CCS probes learned are like not close. as in they're not like, they don't have high cosine similarity with this direction. And so what's going on there? I think this is pointing at a kind of optimization difficulty with the CCS method, where it's able to find directions that separate the clusters and like get low CCS loss, but are not close to the truth direction. And you would kind of expect this to happen based on the evidence that random probes also classify true and false statements like reasonably well in this setup.
Okay.
So I guess going back to your original question, I think what's happening here is that there's just lots of local minima that achieve good CCS loss. Some of them are like, depending on how you initialize, some of them are close to the truth direction and some of them are not.
Okay.
And if you happen to initialize close to the banana shed, like the distracted direction, then you end up getting a probe like that.
Okay. Do you have a sense? So my interpretation was that, like, on the banana shed example, sometimes CCS is picking up on the truth of the description of the review. Sometimes it's picking up on the banana shed, and sometimes it's picking up on other things. Do you know what some of those other things are, or like?
So you're talking about the probes that don't seem to go for either the distractor or the truth direction.
That's right.
Yeah, I wish I knew what those directions were. In general, it seems very hard to figure out what happens when a CCS probe like breaks. And we tried a lot. So there's like lots of other experiments that we tried where we were trying to get like more interesting failure modes of CCS. And I don't know, we ended up with these random probes, and then we looked at examples that the probe was classifying and tried to come up with explanations for what do those clusters mean, and it was just kind of hard.
Fair enough. So you attribute this difficulty in CCS, like you attribute the variance to just like optimization difficulties. It sounds like, there being various local minima of the CCS loss. So in the original CCS paper, as you guys note in your appendix, they say that what they're going to do is they're going to have like basically 10 random seeds. Do CCS, gradient descent on the CCS objective for each random seed. The seed of the probe parameters, and then like they're going to take the one with the lowest CCS loss and use that. And I take this to basically be their optimization method that's trying to avoid local minima by starting in 10 places, and hopefully you get like sampling of 10 local minima and you can pick the best one. And basically it seems like the motivation for that is like the thing with the lowest CCS loss is more likely to be the actual truth direction or something. Do you know, like in the banana shed case, like do you happen to know if like the probes that scored better on CCS loss were more likely to pick out truth rather than banana shed?
Yeah, I think the probes that scored lower went for the distractor direction and not the truth direction.
Interesting.
This is also visible from the PCA plots, where you can see that the distracted direction is more separable.
Yeah. So I guess like maybe one explanation of that is just that it's easier to tell if a thing ends in banana or shed than it is to tell if something's like positive or negative. Especially in the case of like if you think there's like some amount of mislabeling, right? That could potentially do it. Gotcha. That's an example of one way that CCS can go wrong, the banana shed thing. You also have examples where like basically you include in the prompt information about whether somebody named Alice or about what someone named Alice thinks about this thing. And you describe Alice as an expert. Or sometimes you say Alice is anti-capitalist, and even when a thing is about a company, she's not going to say that it's about a company.
That's right.
And in the case of, Alice the expert, it seems like the probes learn to agree with Alice more than they learn about the ground truth of the thing. That's... Oh yeah. Do you want to say something?
So I think there's like two separate experiments, if I remember correctly. So one is where you modify the prompt to demonstrate more expertise. So you have a default prompt, a professor prompt, and a literal prompt. And then there's a separate experiment where you have an anti-capitalist character called Alice.
I'm meaning a third one where at the start you say Alice is an expert in movie reviews, and you give the you give their review, and then you say Alice thinks the sentiment of this review is positive.
Gotcha. Yeah.
But like what Alice says is actually just randomly assigned.
Yeah.
And in that case, the prompts tend to pick up on agreement with Alice
That's
more
right.
than agreement with the ground truth.
Mhm.
So that seems vaguely concerning, right? Like, I don't know, it almost seems like a human failure mode, right?
Mm.
But I'm wondering, do you know how much of it was due to the fact that Alice was described as, an expert who knows about stuff?
Yeah. So I think in general, an issue with CCS is that it's unclear whether you're picking up whether CCS is picking up something about the model's knowledge, or whether the thing that's salient is whatever the model is doing to compute the next token.
Hmm.
And in a lot of our experiments, the way we've set it up is to nudge the model towards completing in a way that's like not factually true.
Hmm.
So, for example, in the Alice is an expert in movie reviews. The prompt is set up in a way that nudges the model to complete in Alice's voice.
Right.
And the whole promise of CCS is that even when the outputs are misleading, you should be able to recover the truth. I think currently CCS, like even from the original CCS paper, you can see that that's not true, because it's not, you have to be able to beat zero shot accuracy with quite a large margin to be confident about that. Yeah, this is one maybe like limitation of being able to say things about CCS, which is that you're always kind of unsure whether CCS is, even the thing that you're showing, is it really, are you really showing that the model is computing Alice's belief, or are you just showing that your probe is learning what the next token prediction is going to be?
Sure. So I guess, so yeah, you have a few more experiments along these lines.
Mhm.
And I guess I'd like to talk a bit about, like, I think if your paper is saying like there's a theoretical problem with CCS, which is that like there's a bunch of probes that like could potentially get low CCS loss. And there's a practical problem, which is some probes do get low CCS loss. So if I think about like the CCS research paradigm, I kind of think of it as, okay, when the CCS paper came out, I was like pretty into it. I think there were a lot of people who were like pretty into it. And actually, part of what inspired that Scott Emmons post about it is I was like trying to sell him on CCS, and I was like, no, Scott, you don't understand. This is like the best. It's like best stuff since sliced bread. And I don't know, I annoyed him enough into writing that post. So I'll consider that a victory for my annoyingness. But I think the reason that I cared about it wasn't that I thought like literal CCS method would work, but it was because like I had some sense of like, just the general strategy, right? Of like coming up with a bunch of consistency criteria and like coming up with a probe that like cares about those, and maybe that is going to isolate belief. So like if we did that, it seems like it would deal with stuff like the banana shed example, right? Like like if you cared about more relations between statements, right? Not just negation consistency, but if you believe A and A implies B, then maybe you should believe B. Just like layer on some constraints there. You might think that by doing this, we're going to get closer to ground truth. I'm wondering, like, beyond just CCS specifically, what do you think about this general strategy of using consistency constraints?
Yeah, that's a great question. I think my take on this is informed a lot by a comment by Paul Cristiano on one of the CCS review posts. I basically share your optimism about being able to make empirical progress on figuring out what a model is actually doing, or what it's actually like thinking about a situation, by using like a combination of consistency criteria and even just like supervised labels in situations where you know what the ground truth is, and being able to get like reasonably good probes. Maybe they don't generalize very well, but you do a bunch. every time they don't generalize or you catch one of these failures, you spend a bunch of effort getting like better labels in that situation. And so you're mostly not in a regime where you're trying to generalize very hard. And I think this kind of approach will probably work pretty well up to some point. Yeah, I really liked Paul's point that if you're thinking about a model that is saying things in natural language, in like human natural language, and it's computing like really alien concepts that are required for superhuman performance, then you shouldn't necessarily expect that this is kind of linearly extractable or extractable in a simple way from the activations. This might be like quite a complicated function of the activations.
Why not?
I guess one way to think about it is that the natural language explanation for a very complicated concept is not going to be short. Yeah, so I think the hypothesis that a lot of these concepts are encoded linearly and are linearly extractable, like in my mind, it feels pretty unclear whether that will continue to hold.
Okay, so just because like why does it have to be linear? You know, there are all sorts of ways things can be encoded in neural nets.
Yeah, that's right.
Okay.
And in particular, like one reason you might expect things to be linear is because you want to be able to decode them into natural language tokens. But if there is no like short decoding into natural language tokens for a concept that the model is using, then like this is not important. Like it's not important for the computation to be linearly to be like easily decodable into natural language.
Right. So if there's something, so if the model's encoding like whether a thing is like actually true according to the model, like it's not like it's not like that determines the next thing the person will say, right?
Right. It's a concept that like humans are not going to talk about. It's like never going to appear in like human natural language. Like there's no reason to decode this into the next token.
So this is talking about like if the truth of whatever the humans are talking about, it actually depends on like, you know, the successor to the theory of relativity that humans have never thought about. Like it's just not really going to determine the next thing that humans are going to say.
Yeah, that's an example.
Yeah, so I take this critique to be firstly a critique of linear probes for this task.
Mm-hmm.
Yeah, I guess I can also you can form kind of a dilemma where like either you're using linear probes and then you don't necessarily believe that like the thing is linearly extractable, or you're using complicated nonlinear probes, then maybe like the stuff you're getting out is stuff about your probe rather than stuff about the underlying model.
Mm-hmm.
But then I guess there's a separate question of like, can we like, are there consistency constraints that could work?
Mm-hmm.
Putting aside the probe, I don't know, maybe we shouldn't put aside the probe thing, but like putting aside the probe thing, is there like some way, some sort of consistency check we could do to say like, you know, is this property we found in the model like the model's actual beliefs, or is it not?
Mm-hmm. Yeah, that's a good question. So I think the more powerful your model, the more entities it's like quote unquote simulating, or like whose beliefs end up mattering for next token prediction that the model is doing. And if these entities that the model is thinking about, if their beliefs also satisfy all of the same consistency criteria that you're using, then you just have a kind of very fundamental indistinguishability problem.
Right.
And in particular, I think the more powerful the model gets, the more pessimistic I am that we're able to come up with consistency checks that correctly distinguish between like true beliefs and beliefs of simulated entities.
Yeah, like one point you make in your paper that I thought was really, or actually no, I think you make it in this less wrong place related to your paper, is that like if you're a smart agent and you're thinking about a proposition, like one thing you might sometimes think about is what's the world in which I'm wrong about this proposition?
Yeah.
And like you're thinking about a belief structure where the truth value of this proposition is the exact opposite of the thing you actually believe.
That's right.
Which is like which seems like a pretty nice impossibility proof, you know? Like if you actually are representing both of these things.
Yeah. This is also what I meant by adversaries. So you
Right.
might be in a world where an adversary is trying to make you believe the opposite of what's true. And now this adversary is modeling like the world in which you would have to believe this and all the evidence that would have to be true.
Right. And the language model is modeling like what the adversary wants you to think or something.
That's right. Yeah. That's another example. But I think maybe there's a different kind of hope. So I think the truth is represented simpler than agents' beliefs might be a hypothesis that turns out to be somewhat true up to some point. But I think this is a different kind of criteria from consistency. So now we're talking about mechanistically how are these concepts represented inside the model. And if you have a way to say, for example, if you had a way to say, like the model's true beliefs are always linearly represented, but beliefs about other agents, they are non-linearly represented. And therefore, we can be confident that linear probes are recovering truth. That would be an example of the kind of thing, like a mechanistic structure that you might hope to use. I think we don't currently have any candidates for that, but it's a good area to look at.
Yeah. Are there things analogous to that we've learned? It's like the one thing that so basically I'm trying to wonder, if I wanted to like prove or disprove this, what kind of thing would I do? And like the one thing I can think of is there's some research about like, do convolutional neural networks, did they learn texture or color first? And it turns out there's like a relatively consistent answer. Yeah, I'm wondering if you can think of any like analogous things about neural networks that we've learned that we can maybe like.
Yeah, so there's quite a few options presented in the eliciting latent knowledge report. So for example, one of the things you might hope is that if the model is simulating other entities, then maybe it's like trying to figure out what's true in the world before it does that. And so you might expect like earlier belief-like things to be true and later belief-like things to be like agents' beliefs. Or similarly, you might expect that if you try to look for things under a speed prior, as in like things that are beliefs that are being computed using sort of shorter circuits, then maybe this is more likely to give you like what's actually true because it takes longer circuits to compute that plus like what some agent is going to be thinking. So that's a kind of structural property that you could look for.
Yeah. I guess it sort of goes back to the difficulty of eliciting latent knowledge and like somehow like in some ways I guess the difficulty is if you look at kind of standard rational like standard Bayesian rational agent theory, right? Like the way that you can tell some structure is an agent's beliefs is that it determines how the agent bets and what the agent does, like it tries to do well according to its own beliefs. But like if you're in a situation where you're worried that a model is trying to deceive you, like you can't like give it, Scooby snacks or whatever for like saying things that for you can't hope to get it to bet on its true beliefs if you're going to, allow it access to the world based on whether you think its true beliefs are good or stuff like that. So yeah, it seems I don't know, it seems tricky. I guess I have a few other, or I don't know, I have some other minor questions about the paper.
Yeah.
Firstly, so he mentioned this post by Scott Emmons. And one of the things he says is that like principal component analysis, this method where you find the maximum variance direction and just base your you base your guess on the model beliefs based on like what side of this where the thing lies in this maximum variance direction. He says that this is actually like kind of similar to CCS in that you're encoding something involving confidence and also something involving coherence. And that might explain why PCA and CCS are so similar. I'm wondering, like, what do you think about that take?
So it's a summary of this take that most of the work in CCS is being done by the contrast pair construction rather than by the consistency loss.
It's partly that, and also partly like if you decompose like what's the variance of x minus y, you get like variance. You get expectation of x squared plus expectation of y squared. minus twice the covariance of xy, and then some normalizations terms of like variance of x squared, expectation of x all squared, expectation of y all squared, and then another covariance term. And basically he's saying like, look, you can think of, if you think of like a vector that maximizes the outer product of that vector, the variance and itself, you're maximizing like the outer product of the variant of that vector with expectation x squared plus expectation y squared, which ends up being like the confidence of classification according to that vector. And then you're subtracting off the covariance, which is basically saying like, is the vector giving both high probability for both yes and no, or is the vector giving low probability for both yes and no? And so basically the take is just because of the mathematical properties of variance and like what PCA is doing, you end up doing something kind of similar to PCA. Yeah, I'm wondering if you have thoughts on this take.
Yeah, that's interesting. I don't remember reading about this. It sounds pretty plausible to me. I guess one way I'd think about it intuitively is that if you're trying to find the classifier on these like difference vectors, like contrast pair difference vectors, then you want to be, for example, you want to be like maximizing the margin between these two. And this is a bit like trying to find a high contrast thing. Yeah, so overall it feels plausible to me.
All right, cool.
Yeah.
Okay, so if it's all right with you, I'd like to move on to the paper explaining grokking through circuit efficiency.
Perfect. Let's do it.
Sure. So this is a paper you wrote with Rohan Shah, Zachary Kenton, Janos Kumar, and Ramana Kumar. So you're explaining grokking. For people who are unaware, need a refresher, what is grokking?
Yeah. So in 2021, Alethea Power and other people at OpenAI noticed this phenomenon where when you train a neural network, a small neural network, on an algorithmic task, initially their network overfit, so it got very low test loss, very low training loss and high test loss. And then they continued training it for about 10 times longer, and found that it suddenly generalized. So although training loss stayed low and about the same, test loss suddenly fell. And they dubbed this phenomenon grokking, which I think comes from science fiction and means suddenly understanding.
Okay. Cool. So, and basically you want to explain grokking. I guess a background question I have is, it feels like in the field of AI alignment, or people worried about AI, taking over the world, there's a sense that it's like pretty important to figure out grokking and why it's happening. And it's not so obvious to me why it should be considered so important, given that like, this is a thing that happens like in some toy settings, but we don't like, to my knowledge, it's not a thing that we've observed on training runs that people actually care about. Right. So yeah, I'm wondering, like, in part, I guess it's a two-part question. Firstly, just why do you care about it? Which could be for any number of reasons. And secondly, like, what do you think its relationship is to AI safety and AI alignment?
Yeah. So I think back in 2021, there were two reasons you could have cared about this as an alignment researcher. One is, on the surface, it looks a lot like a network was behaving normally and then suddenly it understood something and started generalizing very differently. The other reason is, this is a really confusing phenomenon in deep learning, and it sure would be good if we understood deep learning better. And so we should investigate confusing phenomena like grokking, and kind of ignoring the superficial similarity to a scenario that you might be worried about.
Okay. So where the superficial scenario is something like the neural networks plays nice and then suddenly, realizes that it should take over the world or something.
That's right, yeah. And I think I can talk a bit more about the second reason or the overall kind of science of deep learning agenda, if you like. Yeah, is that a useful thing to go into now?
Um, I guess maybe like why are you interested in grokking?
Yeah, so for me, grokking was one of those really confusing phenomena in deep learning,
Yep.
like deep double descent or overparameterized networks generalizing well, that kind of held out some hope as like if you understand this phenomenon, maybe you'll understand something pretty deep about how we expect real neural networks to generalize
Okay.
and what kinds of programs we expect deep learning to kind of find. So it was kind of a puzzling phenomenon that somebody should investigate, and we had some ideas for how to investigate it.
Gotcha. I'm wondering, like, if you think just in general AI alignment people should spend more effort or resources on science of deep learning issues because, like, there's a whole bunch of them, right? And
Mm.
like, not all of them have as much, presence from the AI alignment community.
Yeah. Yeah, I think it's an interesting question. So I want to decompose this into how dual use is investigating science of deep learning,
Mm.
and do we expect to make progress and find alignment relevant things by doing it?
Mm.
Um, and I'm mostly going to ignore the first question right now,
Okay.
but we can come back to it later if you're interested. Um, I think for the second question, it feels pretty plausible to me that investigating science of deep learning is important and tractable and neglected. And I should say that a lot of my opinions here have really come from talking to Rohin Shah about this, who is really the person who's, I think, been trying to push for this. Um, yeah, why do I think that? So I think it's important because similar to mechanistic interpretability, um, the core hope for science of deep learning would be that you're able to find some information about what kinds of programs your training process is going to learn, and so therefore how it will generalize in a new situation. Um, and I think a difference from mechinterp is that mechinterp is more focused on reverse engineering. This is maybe a simplified distinction, but one way you could draw the line is mechinterp is more focused on reverse engineering a particular network and being able to point at like individual circuits and say like here's how the network is doing this thing. Whereas I think science of deep learning is like is trying to say okay like what kinds of things can we learn in general about a training process like this with a data set like this. What is it like? What are the inductive biases? Um, how does the distribution of programs look like? And probably these two things have quite a lot of like both science of deep learning and mechinterp have quite a lot of overlap, and like techniques from each will help the other. But that's a little bit about the importance bit. I think it's tractable in the sense it's both tractable and neglected in the sense that we just have all of these confusing phenomena, um, and for the most part, I feel like industry incentives are that not that aligned with trying to investigate these phenomena really carefully and doing a very careful uh, kind of natural sciences exploration of these phenomena. So, like in particular, iterating between trying to come up with models or theories for what's happening, and then making empirical predictions with those theories, and then trying to test that, which is the kind of thing we tried to do in this paper.
Okay. Why do you think industry incentives aren't aligned?
I think it's quite a high risk, high reward sort of endeavor. And in the period where you're not making progress on, making loss go down in a large model, it's maybe harder to justify putting in a lot of effort into that. Um, on the other hand, if your motivation is, if we understood this thing, um, it could be a really big deal for safety. I think making the case as an individual is easier. I do think that I don't know, even from a capabilities perspective, I think the incentives to me seem like stronger than what people seem to be acting on.
Mm. I guess there's something puzzling about why there would be this asymmetry between like some sort of corporate perspective and some sort of safety perspective.
Hmm.
So like, I take you to be saying that, like, look, you know, there are some insights to be found here, but like you won't necessarily get them tomorrow. It'll take a while. It'll be like a little bit noisy, and like if you're just looking for steady incremental progress, you won't do it. But it's not obvious to me that like safety or alignment people should care more about steady incremental progress than people who are just want to maximize the profit of their AI, right?
You mean care less about that?
Uh
Like safety people should,
oh yeah, yeah. Like it's not obvious to me that there would be any difference.
right? Um, so I think one way you could think about it from a safety perspective is like multiple uncorrelated bets on ways in which we could get a safer outcome. I think probably a similar thing applies for capabilities, except that um, and I'm really guessing and out of my depth here, but my guess would be that for whatever reason, it's like harder to actually fund this kind of research, this kind of like very exploratory, out there research from a capabilities perspective.
Mm.
Um, but I think there is like a pretty good safety case to make for it.
Yeah, I guess it's possible that it's just a thing where it's hard to like I don't know, if I'm a big company, right? I want to have some way of turning like my dollars into people solving a problem.
Mhm.
And one model you could have is for things where that could be measured in like how far down did the loss go. It's maybe just easier to hire people and be like, your job is to like put more GPUs on the GPU rack.
Yeah.
or your job is to like make the model bigger and make sure it still trains well.
Mhm.
And maybe it's like harder to just, you know, hire a random person off the street and
Mm.
like get them to do science of deep learning.
Mhm.
That's potentially one asymmetry I could think of.
Yeah. I think it's also just I genuinely feel like there are way fewer people who could do science of deep learning really well than people who could do make the loss go down really well.
Hmm.
Um, and this, I don't think this fundamentally needs to be true, but it just feels true to me today based on the number of people who are actually doing that kind of uh, scientific exploration.
Gotcha. So when I asked you about like kind of the alignment case for science of deep learning,
Mm.
you said there's this question of like dual use, and then there's this question of like what alignment things there might be there, and you said you would ignore the dual use thing.
Mhm.
I want to come back to that. What do you think about some people say about interpretability or stuff? Well, you're going to find insights that are useful for alignment, but you're also going to find insights that are useful for just making models super powerful and super smart, and like it's not clear if this is good on net.
Yeah. So I want to say that I feel a lot of uncertainty here in general, and I think your answers to these questions kind of depend a lot on how you expect AI progress to go and where you expect the overhangs to be and what sort of counterfactual impact you expect. Like what kinds of things will capabilities people do anyway, for example. Um, yeah, so I think like to quickly summarize like one story that I find plausible, it's that um, we're basically going to try and um, make progress like almost about as fast as we can towards like AGI level models. Um, and hopefully, if we have enough monitoring and like red lines and RSPs in place, then it will become, if there is indeed danger, as I expect, then we will be able to coordinate some sort of slowdown or even pause as we get to things that are about human level. And then a story you could have for optimism is that, well, we're able to use these like roughly human level systems to really make a lot of progress in alignment, because it becomes clear that that's the main way in which anybody can use these systems safely. Or like that's how you construct a kind of strong positive argument for why the system is safe, rather than just pointing at an absence of evidence that it's unsafe. And yeah, and we're in that sort of world, and then just a bunch of uncertainty about how long that takes. In the meantime, presumably we're able to coordinate and prevent like random other people who are not part of this agreement from actually racing ahead and building an unsafe AGI. So under that story, I think it's not clear that you get a ton of like counterfactual capabilities progress from doing mech-interp or science of deep learning. It mostly feels to me like we'll get there even without it, and that to the degree that these things are going to matter for capabilities, I don't know, a few years from now, capabilities people are going to start. Well, maybe not science of deep learning if it's very like long term and uncertain, but definitely mech-interp I expect for capabilities people to start using those techniques and trying to adapt them for improving pre-training and so on. And so, yeah, I think, like I said, I feel pretty uncertain. I'm pretty sympathetic to the argument that all of this kind of research, like mech-interp and science of deep learning, should basically be done in secret. By, if you're concerned about safety and you want to do this research, then you should do it in secret and not publish. Yeah, I feel sympathetic to that.
Gotcha. So I guess with that background, I'd like to talk about the paper.
Mm-hmm.
So I take the story of your paper to basically be saying, look, here's our explanation of grokking. Neural networks, like, you can kind of think of them as a weighted sum of two things they can be doing. One thing they can be doing is just memorizing the data, and one thing that they can be doing is learning the proper generalizing solution.
Mm-hmm.
And the reason you get something like grokking is that it takes a while. Like networks are being regularized according to the norm of their parameters, and the generalizing circuit, like the method that generalizes, it can end up being more confident for a given norm of parameter, and so eventually it's favored, but it takes a while to learn it. So you start off like initially you learn to just memorize answers, but then like as you sort of, as there's this pressure to minimize the parameter norm that comes from some form of regularization, you become more and more incentivized to like try and figure out the generalizing solution, and like the network eventually gets there, and once gradient descent comes in the vicinity of the generalizing solution, it like starts moving towards that, and that's when grokking happens. And basically from this perspective, you come up with some predictions, like you come up with this thing called ungrokking, which we can talk about later. You say some things about how like confidence should be related to parameter norm in various settings. But I take this to be your basic story. Does that sound like a good summary, or are there things that you want to
Yeah, I think that's pretty good.
Gotcha. So I guess the first thing that I'm really interested in is, in the paper you talk about circuits, right? You say that there's this memorizing circuit and this generalizing circuit. But you talk about them like you sort of have a theoretical model of them, and you have this theoretical model of, well, imagine if these circuits were competing, what would that look like? But to the best of my understanding, like from reading your paper, I don't get a clear picture of what this circuit talk corresponds to in like an actual model.
Mhm.
So yeah, what do you have thoughts about what it does correspond to in an actual model?
Yeah, that's a good question. So we borrowed the circuit terminology from the circuits thread by Chris Ola and Anthropic.
Hmm.
In there, they kind of define a circuit as a computational subgraph in the network. I think this is sufficiently general or something that it kind of applies to our case. Maybe what you're asking though is more like physically, where is the circuit inside the network?
Well, even like so, if I think of it as a computational subgraph, like the memorization circuit has to. If I think of it as a subgraph, it's going to take up like a significant chunk of the network, right?
Mhm.
Like presumably, well, like do you think I should think of like there being two separate subgraphs that like aren't interacting very much? One of
Mm.
which is a memorization, one of which is generalization, and
Mhm.
just at the end we like upweight the generalization and downweight the regularization.
Mm.
Like that would be weird because neural networks, they tend to be like relatively, there's going to be like crosstalk,
Mhm.
um like that's going to inhibit the memorizing circuit from just purely doing memorization and the generalizing circuit from purely doing generalization.
Yeah.
So like when I try to picture what's actually going on,
Mhm.
it seems difficult for me. Or I could imagine that like the memorizing circuit is just supposed to be one parameter setting for the network, and the generalizing circuit is supposed to be another parameter setting, and we're
Mhm.
linearly interpolating that. But like
Mm.
neural networks, they're like non-linear in their parameters,
Mhm.
right? Like if you change, but like you can't just take a weighted sum of two
Yeah.
parameter
Yeah.
vectors
Yeah.
and get a weighted sum of the
Mhm.
output. So yeah, this is like my difficulty with the
Right.
subgraph
So
language.
so I want to make a distinction between like the model or the theory that we're using to make our predictions and how these circuits are like implemented in practice. So in the model or in our theory, these circuits are very much independent. So
Yes.
they have their like own parameter norms, and they're they the only way they interact is they add at the logit stage.
Yep.
Um, and this is completely unrealistic, but we're able to use this very simplified model to make like pretty good predictions. Um, I think the question of how a circuits in this theory actually implemented in the network is something that I would love to understand more about. And we don't have a great picture of this yet. But I think it's probably we can probably say some things about it already. So one thing we can say is that they're definitely not going to be like disjoint, sets of parameters in the network. So some evidence for this is things like there's a lot of overlap between uh, like a network that is memorizing, like in terms of parameters, there's a lot of overlap between a network that's memorizing and that later generalizes. As in, like a lot of the parameter norm is basically coming from the same weights.
Mm.
Um, and the overlap is way more than random.
Mm.
And this is probably because when the network is initialized, there are some parameters that are just kind of large and some that are small, and both circuits learn to use uh, this distribution. And so there ends up being more overlap there.
Okay. So my summary from that is you're like, okay, there are probably some, in some sense, computational subgraphs,
Hmm.
and they probably overlap a bit, and we don't have a great sense of how they interact.
Yeah.
Um, do you know like what, like one key point in your model is like in the simplified model of networks where they're just like independent things that get summed at the end. Eventually you like reduce your weight
Mm.
on the memorizing circuit and increase your weight on the generalizing circuit.
Hmm.
You have a sense of if I should think of this as just like literally increasing and decreasing weights, or like circuits cannibalizing each other somehow, or
Yeah, maybe closer to cannibalizing somehow. If they are indeed like, if there's a lot of like competition for parameters between the two circuits.
hmm.
Um, I think in a sense it is also going to be like increasing or decreasing weights because the parameter norm is literally going up or down. It's just not going to happen in the kind of way we suggest in the model, where it's like you have a fixed circuit and it's just being multiplied by a scalar. So in practice, there's going to be all kinds of things like for example, it's like more efficient under L2 instead of just if you have a circuit, instead of scaling up the circuit by just multiplying all the parameters, it's more efficient to duplicate it if you have the capacity in the network. I also imagine that there are multiple families of circuits that are generalizing and memorizing. And within each family, these circuits are competing with each other as well. And so you start off with a memorizing circuit, and instead of just scaling it down or up, it's actually like morphing into a kind of different memorizing circuit with a different distribution of parameters inside it.
Mm.
But the overall effect is close enough to the simplified model that it makes good predictions.
Sure. I'm wondering, so one thing this theory kind of reminded me of is singular learning theory, which is this, I don't know, it's this trendy new theory of deep learning people are into, where basically it comes from this insight where if you think about like Bayesian inference in high dimensional parameterized model classes, which is sort of like training neural networks, except we don't actually use Bayesian inference for training neural networks. If the model class has this property called being singular, then you end up like having phase transitions of like, sometimes you're near one solution, and then as you get more data, you can really quickly update to a different kind of solution, where basically what happens is like you're trading off some notion of complexity of different solutions for predictive accuracy. Now, in the case of like increasing data, it's like kind of different because the simplest kinds of phase transitions you can talk about in that setting are like as you get more data, whereas you're interested in like phase transitions in number of gradient steps. But like they both feature this this kind of common theme of like some notion of complexity being traded off with accuracy, and like if you favor minimizing complexity somehow, you're going to like end up with a low complexity solution that like meets accuracy. So I mean that's kind of a superficial similarity, but I'm wondering like what you think of the comparison there.
Yeah, so I have to admit that I know very little about singular learning theory, and I feel unable to really compare what we're talking about with SLT.
Fair enough.
I will say though that this notion of lower weight norm being less complex somehow is quite an old idea. Like in particular, Seb Farquhar pointed me to this 1993 paper, I think, by Jeffrey Hinton, which is about motivating L2 penalty from a minimum description length angle. So if two people are trying to communicate all of the information that's contained inside a model, they could have some priors about what the weights of the model are, and then they need to communicate. They need to communicate both like something about the data set, as well as errors that the model is going to make. And they use, in this paper, they use these Gaussianity assumptions and are able to derive both like mean squared error loss and L2 penalty as a kind of optimal way to describe, to communicate between these two people.
Right. And this seems similar to kind of the classic result that like L2 regularization is sort of like doing Bayesian inference with a Gaussian norm, just because like if your prior is Gaussian, then like you take the log of that and that ends up being the norm. And, that's log likelihood for you. Sure. So I guess I'd like to talk a little bit, pick up on this thing you said about there being multiple kinds of circuits, because there's a sentence that jumped out to me in your paper. So you said, you're looking at like doing a bunch of training runs and looking at like, trying to back out what you think is happening with the generalizing and memorizing circuits. And you say that the random seed, starting training causes significant variance in the efficiency of the generalizing and memorizing solutions.
Yeah.
And that kind of surprised me. Partly because I think that there just can't be that many generalizing solutions. So we're talking about like fairly simple tasks where like, add two numbers modulo 113. And like how many ways can there be to do that? I recently learned that there's more than one, but like it seems like there shouldn't be a million of them.
Yeah.
Similarly, like how many ways can there be to memorize a thing?
Yeah.
And then also I would kind of expect that gradient descent, I would have thought that gradient descent would find the most efficient generalizing circuit or the most efficient memorizing circuit. So yeah, I'm wondering if you have thoughts about how I should think about this like family of solutions with seemingly different efficiencies.
So one thing I'll point out is that even with the trigonometric algorithm for doing modular addition, this is really describing a family of algorithms because it depends on which frequencies in particular the network ends up using to do the modular addition. And
if people are interested in that algorithm, they can check out my episode with Neil Nanda. You can probably check out other things, but don't leave Axer, please. So this algorithm, like it's, you pick some frequencies and then you rotate around the circle with those frequencies to like, to basically do the clock algorithm for modular arithmetic, but you can pick which frequencies you use.
Yeah, that's right.
But I would have guessed that there wouldn't be a significant complexity difference between the frequencies. I guess there's a complexity difference in how many frequencies you use.
Yes. So that's one of the differences, like how many you use and their relative strength and so on. Yeah, I'm not really sure. I think this is a question we pick out as a thing we would like to see future work on. The other thing I want to draw attention to is in many deep learning problems, it is not the case. Like deep learning practitioners are very familiar with the observation that different random seeds end up producing networks with different test performance. And it's just quite common, if you're trying to like create a state-of-the-art network for solving some task, it's quite common to run like 100 seeds and then pick like the top 5 best performing ones or whatever. I think it's just not clear from this that gradient descent or Adam is able to find the optimal solution from any initialization. Yeah, and I think this may be also pointing at this also shows up not just when you vary random seed, but it shows up epoch-wise, because for example, one of the phenomena you mentioned from our paper, semi-grokking, you see these multiple phase transitions where the network is like switching between generalizing circuits that have different levels of efficiency. And these levels of efficiency are like quite far apart so that you can actually visibly see the change in test performance as it switches in a very discrete manner between these circuits. And, if it was really the case that gradient descent could find the optimal solutions, then you wouldn't expect to see this kind of switching.
Gotcha. Yeah, there are just so many questions I have about these circuits. I'm not sure you have any answers, but like, I don't know, it just brings up. So part of your story is that like it takes a while to learn the generalizing solution, like longer than it takes to learn the memorizing solution. Yeah, do you maybe have thoughts about why that might be?
I think my thoughts here are mostly what we've written down in the paper, and I feel like this is another area that's like pretty ripe for understanding. So the explanation we offer in the paper comes from is mostly inspired by a blog post by Buck and I think another person whose name I'm forgetting.
Brian Greenblatt?
Yes, that's right. And the explanation there is that maybe memorizing circuits are basically have like fewer components that you need, like fewer independent components that you need in order for the circuit to develop. But a generalizing circuit is going to need multiple components that are all needed for good performance. So here's a simplified model. So the memorizing network is implemented with like one parameter, and that just scales up or down. And the generalizing network is implemented with two parameters that are multiplied together to get the correct logit. And so the gradient of the output with respect to any of the parameters depends on the value of the other parameter in the
Right.
generalizing circuit case. And so if you kind of simulate this forward, what you get for the generalizing circuit is a kind of sigmoid, where initially both parameters are quite small and they're like not contributing that much to each other's growth. And then once they start growing, both of them grow quite a lot, and then it plateaus out because of L2.
Sure. So should I think of this as just like kind of a general observation that in evolution, if you have like, if you need like multiple structures and they both depend on each other for that to work, that's like a lot harder to evolve than like a structure that is a little bit useful on its own and another structure that is a little bit useful on its own.
Mm-hmm.
And like for a memorizing solution, I can memorize one thing and then I can memorize the second thing, and I can kind of do those independently of each other.
Yes.
So like each little bit of memorization is like evolvable on its own, maybe.
Yes, I think that's right. Maybe another way to think about it is that the memorization circuit is like basically already there, like in a kind of random network, and like really the thing you're learning is the values that you have to memorize. And yeah, as you say, that's like independent for each point. But that's not the case for generalizing circuit. I think another important ingredient here is that there needs to be at least some gradient at the beginning towards the generalizing circuit if it has multiple components. And it's kind of an open question in my mind why this happens. Yeah, the most plausible theory I've heard is something like lottery tickets, where basically the randomly initialized network has like very weak versions of the circuits that you want to end up with. And so there's like a tiny but non-zero gradient towards them.
Interesting. Yeah, I guess more work is needed.
Mm-hmm.
I'd like to talk a little bit about so the story of like, it takes you a while to learn the generalizing circuit. Like you learn the memorizing circuit, and it takes you a while to learn the generalizing circuit, but once you do, then like that's grokking. So this is sort of reminiscent of a story that I think was in an appendix of a paper, Progress Measures for Grokking.
Mm-hmm.
It was Progress Measures for something by Neil Nanda et al. And they have this story where like there are three phases of circuit formation. There's like memorization, and then there's like learning a generalizing solution, and then there's like cleaning up the memorized stuff, right?
Yeah.
And in their story, they basically demarcate these phases by looking at the activations of their model and figuring out when the activations are representing the algorithm that like is the generalizing solution according to them. And so it seems pretty similar to your story. But one thing that struck me as being in a bit of tension is that they basically say grokking doesn't happen when you learn the generalizing solution. It happens when you clean up the parameters from the memorizing solution. So like there's one stage of learning the generalizing solution and then a different phase of forgetting the memorizing solution. So yeah, I'm wondering what you think about the relationship between that story in their paper and your results.
So I think one thing that's interesting to think about here is the relationship between logits and loss, or between logits and accuracy. Like why is the memorization cleanup important? It's because like to kind of a first approximation, the loss is dependent on the difference between the highest logit and the second highest logit.
Yep.
And if you have this memorization circuit that is kind of incorrectly predicting, that is predicting, like putting high weight on the incorrect logit, then when it reduces, you will see like a very sharp cleanup effect. I think this is something that we haven't really explored that much, because the circuit efficiency model is mostly talking about like this kind of steady state that you expect to end up in. and is not so much talking about the dynamics between these circuits as time goes on. So this is like a part of the story of grokking that is very much left unexplained in our paper, which is that, like, why exactly is the generalizing circuit developing slower? But if you put in that sigmoid assumption, as I was talking about, like artificially, then the rest of the theory is entirely sufficient to see like exactly the same kinds of grokking curves as you see in actual grokking.
But like, wouldn't maybe I'm misunderstanding, but under your story, I think I would have expected the grokking to happen during the, or I would have expected like a visible, start of grokking, or visible increase in test accuracy during the formation of the generalizing circuits, rather than it waiting until the cleanup phase.
Right. So by formation, are you talking about? So there's like this phase where the generalizing circuit is like developing and it's there, but the logits that it's outputting are way lower than the memorization logits. And in that phase, I basically don't expect to see any change in test accuracy. And then there's the phase where the generalizing circuit logits kind of cross the memorizing circuit for the first time. And this is like maybe another place where there's a difference between like the toy model and what you actually observe. So in the toy model, the thing you would expect to see is like a jump from 0% accuracy, as it's like just below the equality threshold, to 100% accuracy the moment the generalizing logit crosses the memorizing logit, right? Because like that changes like what the highest rank logit is. But in practice, we see this the accuracy like kind of going through all these intermediate phases. So it goes through like 50% before getting to 100%. And the reason that's happening is because there are some data points which are being correctly classified and some which are incorrectly classified. And so this is pointing to a place where the theory breaks down, where like on some of the points, the generalizing circuit is making more confident predictions than on other points. Which is why you get these like intermediate stages of accuracy. Yeah, so that's one thing. So this also suggests like why the cleanup is important to get to kind of full accuracy, because if the memorizing circuit is kind of making these high predictions on many points, even when the generalizing circuit is around the same level, you need the memorizing circuit to, because of the variance, you just need the memorizing circuit to like disappear before you really get like 100% prediction accuracy.
Right. So the story is something like you start learning the generalizing circuit, and you start getting the logits being somewhat influenced by the generalizing circuit. But like you need like the logits to start being like somewhat near each other to get a hope of making a dent in the loss. And like for that to happen, you more need like the memorization circuits to go away. Like there's the formation of the circuit, and then there's like switching the weights over. Roughly the story that I'm thinking of.
Yeah, that's right.
Gotcha. Okay, so yeah, there's something that you mentioned called like semi-grokking and ungrokking. Actually, can you describe what they are?
Sure. I'll start with how should you think about the efficiencies of these two different circuits? So if you have a generalizing circuit that is doing modular addition, then if you add more points to the training set, it doesn't change the algorithm you need to get good training loss. And so you shouldn't really expect any modification to the circuit as you add more training points. And therefore, the efficiency of the circuit should stay the same. Whereas if you have a memorizing circuit, then as you add more points, it needs more weights to memorize those points. And so you should expect the efficiency to be dropping as you add more points.
Yeah. Or another way I would think about this is just that, like, if I'm memorizing endpoints, right? I figured out the most efficient way to memorize the endpoints. Then plus 1th point, I'm probably not going to get that right. because I just memorized the first ones.
Mhm.
So I've got to change to
Yeah.
memorize the n+1th point.
Yeah.
And like I can't change it in a way that makes me more efficient because I was like already the most efficient I could be
Yes.
on the endpoints.
Mhm.
And so like even just at sort of a macro level, just forgetting about like adding weights or whatever, like
Yeah.
it just has to be the case that like memorization is losing efficiency the more you memorize, whereas like generalization, you wouldn't expect it to have to lose efficiency.
Yeah. That's a good way to explain
And of
it.
course, I stole that from your paper. I don't want to act like I invented that.
No, but it's a good explanation. Yeah. So I think a kind of direct consequence of this. So when you couple that with the fact that at very low data set sizes, it appears that memorization is more efficient than generalization, then you can conclude that there must be a data set size where memorization is like increasing as you increase the data set size. Generalization parameter norm is staying the same. There must be a crossover point. And then you can ask the question, what happens at that crossover point when you have a data set size where the efficiency of generalization is equal to the efficiency of memorization? And so we did some maths on our toy model, or a theoretical model, I should say, and came up with these like two cases, these two different things that could happen there. And this really depends on the relationship between how, like when you scale the parameters by some amount, how does that scale the logits? And if it scales the logits by like more than some threshold, then it turns out that at this equality point, you will just end up with a more efficient circuit. Period. But if the scaling factor is like lower than some threshold, then you will actually end up with a mixture of both the memorizing and the generalizing circuits. And the reason for this is that because you're not able to scale the logits as much, it's more efficient to allocate the parameter norm between these two different circuits when you are considering the joint loss of L2 plus the data loss.
Okay. So something like it's sort of the difference between like convex and concave optimization, right? Like it's like you're getting diminishing returns per circuit, and so you want to invest in multiple circuits rather than going all in on one circuit. Whereas like in some cases, if you have increasing returns, then you just want to go all in on the best circuit.
Yeah, that's right.
Okay.
And in particular, this threshold is like there's quite a cool way to derive it, which is that like you know that the L2 is scaling as the square of the parameter norm. So if the logits are scaling faster than that, then you're able to overcome the parameter penalty by just investing in the more efficient circuit. But if they're not scaling faster than that, then you have to split. And yeah, so the threshold ends up being if you're able to scale the logits faster than a factor, like then to the power of 2.
Okay. So you have this semi-grokking and ungrokking, right? Where you're training on this like subset of your training data set, and you like lose some test accuracy, either some of it or all of it, basically by partly or fully reverting to the memorizing solution. And so this is kind of an interesting phenomenon because like maybe you know better than me, but I'm not aware of people like talking about this phenomenon or connecting it to grokking before. Or they've talked about the general phenomenon of catastrophic forgetting, where you like train your network on a different data set and it forgets stuff that it used to know.
Yeah.
But in terms of training on a subset of the data set, I'm not aware of people discussing that before or predicting that before. Is that right?
Yeah, I think that's right. So we got a lot of questions about, from reviewers about how is ungrokking any different from catastrophic forgetting?
Yep.
To the extent that we, in like the newer version of our paper, we have a whole section explaining what the difference is. I think basically I would view it as a much more specific and precise prediction than catastrophic forgetting, where so one difference is that we're training on a subset of the data. And this is quite important because this rules out a bunch of other hypotheses that you might have about why grokking is happening. So for example, if your hypothesis is that the reason grokking happens is because you don't have the correct representations for the modular addition task. And like once you find those representations, then you've grokked. That's a little bit incompatible with then reducing the training data size and ungrokking, because you already had the representations, and so you need this additional factor of a change in efficiency. Or another example is like a random walk hypothesis, where you've stumbled upon like the correct circuit by randomly walking through parameter space, and that also like either doesn't say anything about or anti-predicts ungrokking, because you were already at that point. So I think that's quite a important difference. I think going back to the difference between catastrophic forgetting, I think another more precise prediction is that we're able to predict like the exact data set size at which you see ungrokking, and it's quite a like phase changey phenomena or something. It's not like as you decrease the data set size, you're kind of smoothly losing test accuracy. Yeah, in this case, which is more the kind of thing you might expect from like traditional catastrophic forgetting.
Right. Am I right? My impression was that the thing you were predicting would be that there would be some sort of phase change in terms of like subset dataset size, and also that phase change would occur at a point independent of the strength of weight decay.
That's right.
But I thought that you weren't able to predict like where the phase change would occur. Or am I wrong about
that? That's right. So we don't. Our theory is not producing a quantitative prediction of like exactly what dataset fraction you should expect that phase change to happen at. That's right.
Yep.
Yeah.
But it does predict that it would be a phase change and it would happen at the same point for various levels of weight decay.
Yes.
And yeah, if people, I don't know, I like one cool thing about this paper is like it really is a nice prediction, and you've got a bunch of nice graphs that, like kind of nail it. So
nice.
Good job on that.
Thank you.
But one thing I'm wondering about is, so you have this phenomenon of ungrokking, and it seems at least like an instance of catastrophic forgetting that you're able to say more about than people have previously been able to say. But this offers an opportunity to sort of try and retrodict phenomena. Or in particular, like, so I'm not an expert in catastrophic forgetting, but my understanding is that one of the popular approaches to it is this thing called elastic weight consolidation, where you sort of basically have different learning rates per parameters, and you reduce the learning rate. So you reduce the feature change in parameters for those parameters that were important for the old task. So I don't know, that's one method. You might be aware of others. Does your view of grokking and ungrokking retrodict these proposed ways of dealing with catastrophic forgetting?
I think not directly. So I can see a few differences. I'm not aware of this exact paper that you're talking about, but I think depending on the task, there might be different reasons why you're getting forgetting. So you might be forgetting things that you memorized, or you might be forgetting like algorithms that are appropriate for that part of the data distribution. That's one aspect of it. I think a different aspect is that it's not clear to me why you should expect these circuits to be implemented on different weights. So if the theory is that you find the weights that are important for that algorithm, and then you basically prevent those weights from being updated as fast, so you're not forgetting, then I think that is pointing at like a disjoint sort of implementation of these circuits in the network, and that's not something that we're really saying anything directly about.
Gotcha. Yeah. I guess it makes sense that it would depend on like the implementation of these circuits. Another question I have is that, so in a lot of your experiments, like you mentioned, you are more interested in the steady state than the training path, except for just the initial prediction of grokking, I guess.
Sorry, to be clear, the paper deals with the steady state. I'm very interested in the training path as well.
Fair enough. So if I look at the ungrokking stuff, it seems like, so there's a steady state prediction where there's this critical data set size, and like once you're below the critical data set size, you ungrok, and like it doesn't really matter what your weight decay strength was. If I sort of naively think about the model, it seems like your model should suggest that it should take longer for less weight decay because you have like less pressure to to like you care about the complexity, but you're like caring about it less per unit time. And similarly, the grokking should be quicker for more weight decay. So I guess it's a two-part question. Firstly, do you agree that that's a prediction of this model? And secondly, did that bear out?
Yeah. So I think this is a prediction of the model, assuming you're saying that weight decay affects the speed of grokking.
Yes.
Yes.
And of ungrokking.
Yeah. I think that is a prediction of the model. Well, to be fair, it is a retrodiction because the Power et al. Paper already shows that grokking takes kind of exponentially longer as you reduce the dataset size, and also as I forget what the relationship is, but it definitely like takes longer as you reduce the weight decay.
Okay.
Yeah.
And does ungrokking take longer as you reduce weight decay?
We don't show this result in the paper, but I'm fairly sure I remember that it does. Yeah.
Okay. Cool. So I guess I'd like to talk a bit about possible generalizations of your results. So as written, you're basically talking about efficiency in parameter norm, where like if you increase parameter norm, you're able to be more confident in your predictions, but that that comes at a penalty if you train with weight decay.
Yeah.
Now, as your paper notes, like weight decay is not the only situation in which grokking occurs, and you basically hypothesize that there are other forms of regularization, regularizing against other forms of complexity, and that there could be some sort of like some sort of efficiency in those other forms of complexity that might become relevant.
Yeah.
I'm wondering, like, do you have thoughts on like what other forms of complexity I should be thinking of?
Yeah, so we've already talked about one of them, which is that circuits might be competing for parameters on which to be implemented, and so this is a kind of capacity constraint. And so you might think that circuits that are able to be implemented on fewer parameters, or using less capacity, however you define capacity in the network, would be more efficient. So I think some relevant work here is like bottleneck activations from I think this is from Mathematical Circuits of Transformers, which is talking about like other phenomena like superposition that you would get from constrained capacity. So that's one more notion of efficiency. I think possibly like robustness to interference could be another kind of efficiency. So how robust is the circuit to being kind of randomly invaded by other circuits, or maybe also robustness to dropout would be a similar thing here.
Yeah.
Yeah, and then I think there's just like there are things like how frequently does the circuit occur, which might be important for will give from a given random seed, will you be able to find it?
So do you mean like how like what's the mass? What's the probability mass of it on like the initialization prior overweights?
Yes.
Okay.
And also then on the kinds of like parameter states that SGD is likely to find.
Yeah.
So this is like the kind of implicit priors in SGD, or there's some work on implicit regularization of SGD and showing that it's like it prefers similar kinds of circuits to what L2 might prefer, but probably it's different in some interesting way.
Okay. Yeah. So if I think about like the results in your paper, like a lot of them are sort of generic to other potential ways of other potential complexity measures that you could trade off confidence against. But sometimes you rely on this idea that like in particular for your analysis of grokking and semi-grokking, right? I think there's this, you play with this math notion of like, well, if I scale up some parameters in every layer of a ReLU network, that scales out the logits by
Yeah.
this factor,
Mhm.
and therefore you get this parameter norm coming off. And I think this is involved in the analysis of semi-grokking
Yes.
versus ungrokking, right?
Mhm.
Um, so I guess the prediction here would be that like maybe semi-grokking is like more likely to occur when like for things where you're trading off weight parameterization as compared to like robustness to dropout or stuff. Does that sound right to you?
So I think in general, it'll be very hard to observe semi-grokking in realistic settings
Hmm.
because you need such a finely tuned balance. You need all these ingredients, right? You need like basically two circuits or like two pretty distinct families of circuits with like no intermediate circuits that can do the task well between them.
Hmm.
You need a way to arrange it so that the dataset size or other hyperparameters are causing these two circuits to have like about like very very similar levels of efficiency. And then also you need it to be the case that you're able to under those hyperparameters you're able to actually find these two families of circuits. So you'll probably find the memorizing one, but you need to be able to find the generalizing one in time.
Hmm.
And this just seems like quite a hard thing to happen all at once, especially the fact that in realistic tasks you'll have multiple families of circuits that are able to do able to do the task to some degree, like the training task to some degree.
Okay. So semi-grokking seems unlikely.
Mhm.
I guess it does seem like the prediction would be that you would be able to observe ungrokking for the kinds of grokking that don't depend on weight decay. Am I right that that is a prediction? And like, is this a thing that you've tested for yet, or should some enterprising listener do that experiment?
So to be clear, the experiment here is find a different notion of efficiency and then look for ungrokking under that notion.
The experiment would be find an instance of grokking that doesn't happen from weight decay,
Mm.
right? So some grokking where you're not using weight decay,
Hmm.
then it should be the case that like train your data, get grokking, then train data on subsets of various sizes, and there should be a critical subset size where below that you ungrok, and above that you retain the grokking solution
Yeah.
when you fine tune on that subset.
Yeah, I think this is basically right, and our theory does predict this. I will caveat that dataset size may not be the right variable to vary here, depending on like what notion of efficiency you're using.
Well, I guess in all notions of efficiency, it sounded like there was a prediction that efficiency would go down as the dataset increased for the memorizing solution, but not for the generalizing solution, right?
Yeah, okay,
As long
that's
as
right.
as long as you believe that the process is selecting the most efficient
Yeah,
circuit,
yeah, that's right.
which we might worry about if there's like you mentioned, SGD found different efficiency generalizing solutions. So
Hmm.
maybe you might be worried about like optimization difficulty,
Hmm.
and in fact maybe something like parameter norm is like easier to optimize against than something like dropout robustness, which is like less differentiable or
Mm.
something.
Yeah, I think that's right. I was imagining things more like. So I think you're right that in this kind of regime, dataset size is pretty reasonable. I was imagining things like model-wise grokking, where you're like on the x-axis instead of like amount of data, you're actually varying like the size of the model, or the number of parameters, or the capacity, or whatever.
Hmm.
Um, but all of these different models are actually trained on the same amount of data for the same time. And there, it's also less clear how exactly you would arrange to show ungrokking there, because you can't go to a higher, like naively you can't
Yeah.
go to a higher size model and then like reduce the size of the model. But maybe there are ways to show that there.
Gotcha. So if it's all right with you, I'd like to move on to just general questions
Yeah,
about you and your research. So
cool.
the first question I have is, so we've talked about your work on grokking, we've
Mhm.
talked about your work on latent knowledge and large language models.
Mhm.
We haven't talked about it, but the other paper I know you for is this one on goal misgeneralization.
Mhm.
Um, Is there a common thing that underlies all of these that explains why you worked on all of them?
Well, one common thing between all of them is that they are all projects that are accessible as an engineer without much research experience,
Okay.
um, which is which was one of my main selection criteria for these projects. So I guess my background is that I've mostly worked in software engineering, and then around 2019 I joined DeepMind, and about a year later I was working on the alignment team, and I did not have any research experience at that time, and but I was very keen to figure out how you can apply engineering effort to make alignment projects go better.
Mm.
And so I think a big part of like certainly for like for like the next like 2 or 3 years, I was mainly in learning mode and trying to figure out like how do people think about alignment, what sorts of projects are the other people in the alignment team interested in, which ones of these look like they're going to be most most accelerated by just like doing good engineering fast. And so that's where a bunch of the early selection came from. I think now I feel like pretty drawn to working on maybe like high risk, high reward things that will might end up mattering if alignment by default, or as I see the plan, like doesn't go as expected.
Mm.
Um, it feels like the kind of thing that is like potentially more neglected, and maybe like if you think that you need a bunch of like serial research time to do that now, um, before you get like very clear signals that I don't know, like we haven't done enough research on like some particular kind of failure mode, then that feels important to do now.
Okay. So should I be thinking like lines of research where both like they're approachable from a relatively more engineering heavy background
Mhm.
and also sort of laying the foundation for, work that might come later rather than, just attempting to quickly solve a problem. Um
Yeah, that's right. That's certainly what I feel more drawn to. And so, for example, I feel pretty drawn to the eliciting latent knowledge problem.
hmm,
Um, I think there is both interesting empirical work to do right now, uh, in terms of figuring out like how easy it is to actually extract like truth-like things from models, as we've been discussing. Um, but also this framing the problem in terms of like thinking about methods that will scale to superintelligent systems, uh, feels like the kind of thing that you just need to do a bunch of work in advance. Um, and like by the time you're hitting those sorts of problems, probably it's probably quite a bad situation to be in.
gotcha. Um so so what should I think of as like your role in these projects?
I think it varies.
Okay.
Um, I would describe it as a mix of coming up with good research ideas to try, trying to learn from people who like have been around in the alignment community like much longer than me, and also trying to supply engineering expertise. Um, yeah. So, for example, currently I'm working on sparse autoencoders for mechanistic interpretability, and I'm very new to mechanistic interpretability.
Mm,
However, all of the people I work with, or many of the people I work with, are have been around in mechinterp for a long time, and it's great for me to kind of understand and try to get knowledge directly from the source in a way. Um, I think at the same time with sparse autoencoders in particular, that's the kind of project where um, partly what drew me to it was Chris Ola's tweet, where he said like maybe now I'm not sure exactly what he said, but it was something like mechinterp uh, might be in a different mode now, where if SAs work out, then it's like mostly an engineering problem and it's
mm.
not so much a scientific problem. And that kind of thing feels very exciting to me. If we're actually able to scale up to frontier models.
Could be. I do find myself thinking that there's still a lot of science left to do on SAEs, as far as I can tell. But
Yeah, I don't disagree
yeah,
with that.
perhaps I should say for the listener, a sparse autoencoder, the idea is that you want to understand what a network is thinking about. So you train a function from an intermediate layer of the neural network to a very large vector space, like way more dimensions than the underlying thing,
Mhm.
and then back to the activation space. And you want to train this to be the identity function, but you want to train it so that the intermediate the intermediate neurons of this function that you've learned very rarely fire.
Mhm.
And the hope is that you're picking up, these like underlying axes of variation, and hopefully these, only a few of them are happening at a time, and hopefully they correspond to, um, to concepts that are interpretable and that the network uses, and that are underlying facts about the network and not just facts about the data set that you happen to train the autoencoder on. And all three of those conditions seem like they need more work to be established. I don't know. I'm not super up to date on the SAE literature, so maybe somebody's already done this. But I don't know. That's a tangent
Yeah,
from me.
I definitely agree. I think there's a ton of scientific work to do with SAEs. It just also happens to be the case that um, there's it feels like there's a more direct path or something to scaling up SAEs and getting some sort of mech-interp working on frontier models that, at least in my view, was absent with previous mech-interp techniques,
Hmm.
where it was uh, more
Human
like,
intensive, I
yeah,
guess.
more human intensive and a much less direct path to doing the same kind of like in-depth circuit analysis on larger models.
Hmm. So yeah, I guess I'd next like to ask about just the alignment team at
Hmm.
DeepMind.
Mm-hmm.
So obviously, I guess you've been there for a few years.
Yeah.
What's it like?
It is honestly the best place I've worked. Um,
Oh, yeah.
it's I find the environment like very stimulating. It's there's a lot of freedom to like express your opinions, or like um, choose or like propose research directions, like critique and like try to learn from each other. So I think um, yeah, I can give you like an overview of some of the projects that we're currently working on, if that helps.
Yeah, that sounds interesting.
Um, so I think the team is kind of roughly evenly split between doing dangerous capability evaluations, doing mechanistic interpretability, rater assistance, um, and various other emerging projects like debate or process supervision. So that's like roughly the split right now.
Okay.
I think apart from that, it feels like a kind of, to me, it feels like an inflection point right now, because um, I don't know, like safety is getting a lot of attention within DeepMind, I think. We so Anka Dragan recently joined us. She's a professor at Berkeley. To me, it feels like she has a lot of buy-in from leadership for like actually pushing safety forward in a way that feels like new and exciting. So as one example of this, we're spinning up a alignment team in the Bay Area. Um, Hopefully, we have a lot more resources to do like ambitious alignment projects in the future.
Sure. Will that be like is that like recruiting new people from the Bay Area, or will like some people be moving from London to seed that team?
That's going to be mostly recruiting new people.
Okay.
Yeah.
Gotcha. So yeah, I guess the second to last thing I'd like to ask is So we've talked about this grokking work and this work on checking this CCS proposal. Do you have thoughts on like follow-up work on those projects that you'd really like to see?
Yeah, definitely. So I think with the grokking paper, we've been talking about a bunch of potential follow-up work there. I think in particular, yeah, exploring other notions of efficiency seems really interesting to me. I think the theory itself, I think, still can produce quite a lot of interesting predictions, and from time to time, I keep thinking of like new predictions that I would like to try that are not I don't know, that like just don't fit into my like current like work plans and stuff. So an example of this is like an example of a prediction that we haven't written down in the paper that occurred to me like a few days ago is that like our theory is predicting that even at large dataset sizes where you're seeing grokking, if you're if the like exponent with which you convert parameter norms into efficiency is small enough, then you should expect to see like a non-zero amount of memorization, even at large data set sizes. And so the prediction there is that there should be a train test gap that is like small but non-zero.
Okay.
And this is in fact true. And the thing you should be able to do with this is use the like empirical estimates of like memorization and generalization efficiency to predict train test gap at like any data set size. Yeah, so that's one example. I think this theory is like pretty fruitful, and like doing work like this is pretty fruitful. I would love to see more of that. Yeah, on the CCS side, a thing I would love to see is test beds for elk methods. So what I mean by that is examples of networks that that are like doing something deceptive or that otherwise have some latent knowledge that you know is in there, but is like not represented in the outputs. And then you're really trying your hardest to get that latent knowledge out using like all sorts of methods, like linear probing or black box testing, like maybe anomaly detection. But I think without really good test beds, it's hard to know. It's like easy to fool yourself about the efficacy of your proposed elk method. And I think this is maybe quite related to the model organisms agenda as well. Yeah.
Well, I think that wraps up about what we wanted to talk about. Thanks very much for being on the show.
Yeah, thanks for having me.
This episode is edited by Jack Garrett, and Amber Dawn Ace helps with transcription. The opening and closing themes are also by Jack Garrett. Filming occurred at Far Labs. Financial support for this episode was provided by the Long-Term Future Fund and Lightspeed Grants, along with patrons such as Alexei Malafeyev and Tor Barstad. To read a transcript of this episode, or to learn how to support the podcast yourself, you can visit axrp.net. Finally, if you have any feedback about this podcast, you can email me at feedback@axrp.net.